Ask an AI a simple question, and it performs well. Ask that same model to cross-reference multiple documents to execute a complex, multi-hop query, and the system fails. GraphRAG applications solve this problem. Standard retrieval augmented generation depends on semantic vector similarity. It converts the user's prompt into numerical coordinates and retrieves text that maps closely to that position in a multidimensional space. The limit of this approach is that vector stores retrieve independent chunks of text. They rank paragraphs by relevance to the prompt, but they lack the relational context needed to link those paragraphs together. Without a map of these relationships, the language model predicts connections based on word probability alone. This lack of structural constraint leads to hallucinations when the model is forced to resolve complex enterprise queries. To achieve reliable enterprise-grade agentic AI, we have to transition from flat vector stores to structured knowledge graphs. Deterministic reasoning requires a system where entities are explicitly connected by verifiable relationships. It cannot rely on the probabilistic word prediction of a standard LLM. We analyze the Neo4j data model, write cipher queries to extract information, and build a complete GraphRAG pipeline. Large language models are mathematical engines. Their output is bounded by the dimensional, queryable reality they use for grounding. The foundation of this system is the labeled property graph architecture. It differs from traditional relational SQL databases in its internal structure. In a SQL environment, finding connections requires multiple join operations. The database scans entire tables to create temporary results, which leads to high computational costs and memory inefficiency. In the Neo4j model, data is stored as individual nodes and the edges that connect them. Both the nodes and those connective edges store specific key-value properties directly within the structure. This enables a feature called index-free adjacency. Instead of scanning a massive index file to find the next record, an operation that takes longer as the dataset grows, index-free adjacency uses direct memory pointers. The system jumps from one node's address to the next in constant time. Because the database skips index lookups, it can execute massive, real-time multi-hop queries. A relational database would crash attempting the same traversal at scale. This memory efficiency at the hardware level is what makes mapping millions of AI relationships possible. Before an AI can use this graph, unstructured data, like a PDF, must be parsed into a strict database schema. The process starts by running text through a model trained for named entity recognition. The algorithm isolates discrete subjects and extracts them as nodes. These extracted entities map directly to a cipher merge statement. This populates the database with the initial structure of the graph. The graph is then enriched using cipher commands to append specific properties and metadata to existing nodes. This ingestion process translates unstructured human language into a mathematically strict, programmatic environment. This diagram shows the architecture utilizing graph cipher QA chain to connect the language model to the database. Step 1 begins at the top layer with natural language. Step 2, the LLM generates a cipher query. Step 3, Neo4j executes the traversal. High-fidelity, explicitly linked contextual data is then returned to the LLM to ground its final generated answer. This architecture abstracts the database complexity, creating an autonomous reasoning loop for the user. We can see this in a high-stakes scenario using the SNOMED-CT clinical dataset. Here, a single medical concept is uniquely defined by its concept ID and specific descriptions. SNOMED-CT utilizes semantic triples to mathematically define clinical meaning. Concept A triggers a relationship that leads directly to concept B. Unlike standard LLMs that associate symptoms via text proximity, this graph model enforces a multi-hop logical path proving causality. Enforcing these diagnostic pathways serves as an absolute guardrail against medical AI hallucinations. Deterministic relationship graphs are the only reliable way to constrain probabilistic language models in mission-critical environments. This exact logical constraint remains perfectly precise even when it is scaled to massive enterprise datasets containing billions of relationships. At this scale, we can use graph algorithms like community detection to pre-compute new metadata and feed those insights back into the LLM. NASA applied this architecture to organize decades of records, as seen in this historical logs mission control room. At enterprise scale, graph architectures surface hidden engineering relationships, identifying connections that save millions of dollars. The technology is moving from pattern-matching text predictors to systems backed by explicit, queryable maps of institutional knowledge. Standard vector search remains the absolute optimal mechanism for quickly finding the initial semantic starting point of any complex query. Graph traversal is the mechanism required to execute reasoning across the connected data located at that starting point. Integrating semantic vector search with structural graph traversal is the mandatory architecture for next-generation enterprise AI.